Good morning, friends. Myself Shashikant Goilkar, Professor Mechanical Engineering Department of Fenolus Academy of Management and Technology, Ratnagiri. Today we are going to learn about the components of simple vibratory systems. Today we will take, for example, as practical examples which we see in our day-to-day life. Let us take example of a motorbike which consists of a spring. You may be familiar with this type of physical configurations. In this case, the spring provides a restoring force along its line of action, and here the mass of rider and the bike is considered as a combined mass of the system. So here there are two parameters like spring and mass. So let us consider, we will not go into the complications, so we will consider first of all the free vibratory systems. So if we write equation of motion for this, then we can write it as like this. The physical configuration can be converted into a schematic representation, and we can provide the corresponding nomenclature. Let us take for spring we will consider it as a K, and for mass we will consider it as a M. So in this case, the inertia force, there are forces. There are two forces now associated with this. Let us forget about the air resistance caused during the system into the system. So here we will consider it as K as a spring, which is a resisting force provided by the spring, and mass is a combined mass of rider and the motorbike. So here, due to this mass, there will be a inertia force that will be determined, or that will be explored as a mx double dot, that will be mass into its acceleration, and the restoring force will be provided by a spring with its deflection along the linear direction, that is x. So together, when we consider the equilibrium of forces, then resultant should be equal to 0. So if we consider all the associated forces, then it becomes, the equation of motion becomes mx double dot plus kx is equal to 0. So in case of simple linear spring mass system, the equation of motion becomes as mx double dot plus kx is equal to 0. So let us take another example, physical configuration, that is the torsional spring mass system. So here we can take a configuration. You can see that this is a propeller shaft of a ship or marine engines. So here the propeller shaft acts as a disc. It is considered as a disc, and it is connected with the shaft, driving shaft. So together this we can consider as a disc attached to a shaft. So this is one, and this shaft undergoes a twisting moment because of the rotation of the propeller. Another example is, we can take it as another physical configuration, rather we can take it as flywheel and a shaft system. So here the flywheel is connected to this shaft. So this flywheel we can consider as a disc, and the shaft we can consider as a linear shaft which is connected to this flywheel. Now together we can consider this as again configuration as disc connected to a shaft. So let us express this in terms of a schematic representation. We can write it as the shaft which is connected to the disc. It will have a restoring force generated with its torsional stiffness. It can be denoted as KT, torsional stiffness, and whenever the disc undergoes torsional twist, then it can be indicated by a theta in twisting angle theta. So here the J is the moment of inertia of this mass moment of inertia of the disc. So here we can write the inertia force in the form of J theta double dot, and spring force, restoring spring force, we can consider it as KT theta. So when we consider the equilibrium equation, then it will become like J theta double dot plus KT theta equal to 0. So this becomes equation of motion in terms of the for the system, the physical configurations which are considered as a torsional spring mass system. So these are the, we can see that the equation of motion way of representing the physical configurations in the mathematical form, that is the equation of motion of the linear spring mass system as well as the torsional spring mass system. Thank you very much.